Greetings, it's Paul Bamberg with the introductory video for Class 14 of Math 117. This should be a little shorter than the previous video, largely because I'm leaving out a lot of details of the proofs. So let's get started. A lot of times one can compute expectations by summing series, perhaps infinite series. Doing this is a standard activity in introductory probability courses. And so let's imagine that we've got a countable sample space. Could, for example, be the integers or the positive integers. Our sigma field is going to be the largest possible choice, namely 2 to the omega, the power set of that, and we have some probability measure p. This sigma field is uncountable, but that doesn't really cause us any serious trouble. Because our sigma field is so large, any function is necessarily also a random variable. Not necessarily positive, though, so in order to calculate the expectation of one of these random variables, we have to write it as the difference between x plus and x minus, calculate the expectation separately, and combine them. And if both these expectations are successfully computed as the sum of convergent series, then we've got an integrable random variable, and we can conclude the result that Deneen states as proposition 7.1. First, the random variable x is integrable if and only if its absolute value is integrable, and in that case we can compute its expectation by simply summing over the countable sample space the value of the random variable for each element omega sub n in the space multiplied by the probability that the random variable, that the probability of the set consisting of the single element omega sub n. And I remind you again, the series has to be absolutely convergent. If it's conditionally convergent, you can compute the sum, but it doesn't define the expectation. Now let me remind you about rules for reordering series. If you've got a conditionally convergent series and you change the order in which the terms are summed, you can change the sum of the series. That is, you can change the limit of the sequence of partial sums. You can't do that for absolutely convergent series, and Deneen has a short, clever proof of that fact. He says, from our random variable, let's make a new random variable, y sub m, where we set the value equal to 0 for all but the first m terms of the reordered series. That is, you have proposed to sum the series in a different order, and in y sub m, you select terms from the original series that correspond to the first m terms of the reordered series. Clearly, this sequence will approach the random variable x pointwise, because as m goes to infinity, eventually every term is going to get included. Equally obviously, the sequence of absolute values for y sub m is dominated by the sequence of absolute values, and we know that this is integrable. So the dominated convergence theorem says the sequence of expectations for y sub m converges to the expectation of the random variable x. In other words, we get the same answer by summing the terms of the series in some different order. If you have two absolutely convergent series and you form their product, then you're summing over the set of pairs of integers, but that's just another countable set, and the sum can be done in either order. Deneen actually uses that fact to prove that the exponential of the sum is the product of the exponentials. We did that in the very first class by using Taylor series. And he also shows by computing an appropriate double sum that the expectation of a Poisson distribution is equal to its parameter. Now let me remind you of some little facts from real analysis. You've almost certainly encountered these results before. You may or may not have learned how to prove them, but we won't worry about that at the moment. We've got a continuous function from a closed interval to the real numbers. Probably the best known of all these results is the intermediate value theorem. If either the function is negative at a and positive at b, or positive at a and negative at b, so the product of those two values is 0, then there must be some value c in the interior of the interval, not necessarily unique, where f is equal to 0. Second property, if I is an interval, could be open, could be closed, could be open at one end, closed at the other, the set of function values for x in that interval is also an interval. A continuous function maps intervals into intervals. And in fact, if the interval is the closed interval from a to b, then its image is going to be the closed interval from some little m, a minimum, to some capital M, a maximum. In other words, for a continuous function on a closed interval, the function always has a minimum, has a maximum, has a point where it achieves its minimum value and a point where it achieves its maximum value. If the function is one-to-one, then either it's strictly increasing or strictly decreasing. And finally, on a closed interval, there's no difference between continuous and uniformly continuous. Now, let's recall the definition of independent events. Probability of the intersection is the product of the probabilities. Let's recall the definition of independent random variables. Every event in the sigma field generated by x is independent of every event in the sigma field generated by y. And you proved in class a while back that if x and y are independent simple random variables, the expectation of the product is the product of the expectations. But the converse is not necessarily true. Another thing that was done in class is to look at an example where, although the expectation of the product equaled the product of the expectations, the random variables in question were not independent. Suppose we want to go from simple random variables to the more general case of integrable random variables. Deneen does this, and he proves it in the obvious and rather tedious way. First, he represents positive integrable variables as limits of simple random variables. You know the trick for doing that. He then writes the random variables as differences of their positive and negative parts, does a bunch of algebra, and proves yet again the expectation of a product is the product of the expectations. If you try to prove this from scratch, it becomes rather a pain because you can't simply write down a sum and factor it. That only works for simple random variables. Now let's think about functions of random variables. To be precise, let's think about Borel measurable functions. What does Borel measurable mean? It means that if we start with any Borel set B, the inverse image, the set of values that get mapped into B by the function, is also a Borel set. And Deneen proves that the following three conditions are equivalent. The random variables are independent. For any pair of Borel measurable functions of these random variables, the expectation of the product of the functions is equal to the product of the expectations. And finally, if you restrict this just to bounded Borel measurable functions, that's good enough. I am going to outline the proofs of these three things on the next slide, so bear in mind what they are. Independent random variables, any pair of Borel measurable functions, any pair of bounded Borel measurable functions. But first, let's look at the standard counterexample. You're playing in a fair casino, and every time you play, you either win $1 or lose $1, each with probability of half. And for 2 plays, I can define a pair of random variables. X is the total amount won. Clearly, the expectation of that is 0, because you're as likely to win or lose on each play. And your improvement, the winnings on the second play minus winnings on the first, has expectation 0, for the simple reason you're as likely to do worse on your second play as you are to do better. If you take x times y, you get a random variable that is equal to 0, because if you do the same thing on both plays, then your winnings don't change between the 2 plays, and y is 0. If, on the other hand, you have +1 followed by -1, or the other way around, the total amount you won is 0. So it's rather trivially true the expectation of the product is equal to the product of the expectations. Equally clearly, the random variables are not independent. If the total amount that you won is equal to 0, you must have done either better or worse on the second play than on the first play. But in this case, it is not true, and that's the point of the example at the moment, that arbitrary functions satisfy the rule expectation of the product is product of the expectations. The functions I choose are just the squaring function for both x and g, and you can easily compute x squared, y squared, and x squared times y squared. What you find when you do that is that, for example, if you win both times, x squared has the value 4, y squared has the value 0, x squared times y squared has the value 0, and in that case, f of x times g of y will turn out to have an expectation of 0. The expectation of x squared times y squared is 0, but the expectation of x squared itself is 2. It can't be negative. The expectation of y squared can't be 0. Can't be 0 because this random variable is never negative. So the expectation of f of x is 2. The expectation of g of y is 2. The product is 4. 4 is not equal to 0. More generally, it's not hard to show that the 3 conditions I mentioned 2 pages back are independent. Recall that when you take a function of a random variable x, you generate a sigma field that may be smaller but can't be larger. The sigma field may be smaller because, for example, if you use the squaring function as f, you may combine the level set for +2 and the level set for -2 into a single level set for the square is equal to 4. So that shows that independence implies expectation of the product is product of the expectations for arbitrary Borel measurable functions. The set of bounded random variables is a subset of the set of integrable random variables, so this is also rather trivially true for bounded random variables. And to show that the third condition implies the first one, you do the same thing we did before in a very similar proof. As your f and your G, you just choose indicator functions for sets A and B, which translates the result into the condition for independence. Now suppose you want to calculate the expectation of a continuous function G of a random variable x. The efficient way to do it is just to calculate the Lebesgue integral over real numbers of G with respect to the probability measure P sub x. And there's not really much to the proof of this. You start by proving it for simple Borel measurable functions. Then you have to split the function G into positive and negative parts, construct some increasing sequences, and apply the appropriate theorem. Frequently, it turns out to be useful to work with the square of some quantity rather than the absolute value of that quantity. In other words, it's often easier to calculate the expectation of x squared than the expectation of the absolute value of x. And in fact, there's a name for the set of random variables, which is in fact a vector space, for which the expectation of the square is finite. This is called big L2. It turns out that anything that belongs to big L2 is also an integrable random variable. In other words, if the expectation of the square is finite, the expectation of the original of a random variable is also finite. Now you might say, that's pretty obvious, isn't it? The square is bigger than the original number. Well, not quite. That's true for anything that's 1 or larger. It's not true for numbers less than 1. And Deneen's proof exploits the value 1 to fix that. It says, let's consider the subset of the sample space for which the random variable has an absolute value less than or equal to 1. And let's define a new random variable that equals 1 on this set. Otherwise, it equals x squared. Now, if x squared is integrable, y is also going to be integrable. But now we see that the absolute value is always less than y. When the value is 1 at some point in the sample space, this is true because a number that is greater than 1 is less than or equal to its square. If, on the other hand, x has an absolute value less than 1, y was defined to have the value 1 to make this true, and that proves that x is also an integrable random variable. Now some very standard terminology, which you very likely knew before ever starting this course. If x is a random variable, we can denote its expectation by mu if there's only one random variable around, or mu sub x if we're considering several random variables. The variance is defined then to be the expectation of the square of the quantity x minus mu. It's usually denoted by sigma squared, which lets us use sigma to denote the so-called standard deviation. And here are some properties, some of which you'll prove in class. Very useful result. You can always compute this by calculating the expectation of x squared and then subtracting the square of the expectation of x. If you have independent random variables, their covariance, which is the expectation of x minus its expectation by y minus its expectation, is 0. If two random variables are independent, the variance of the sum is equal to the sum of their variances. This is a slightly surprising and very useful result, and it clearly extends from two random variables to any finite number of random variables by induction. Finally, if you have n random variables that all have the same expectation and all have the same variance, and you form their average by adding them up and dividing by n, you get a random variable that has the same expectation, but that has a variance that's smaller by a factor of n. I'll conclude with a trivial but very useful inequality called Chebyshev's inequality. This is one of these mathematical results that is basically a one-liner, but is so useful that it nonetheless bears the name of a famous mathematician. The utility of Chebyshev's inequality is that if we know the variance of a random variable, capital X, we can put an upper limit on the probability of extreme values, of the probability that its event is more than some number of standard deviations away from the mean. In other words, we can put a restriction on the size of the tails of the probability distribution. To prove this, let me denote by A the event that we are at least t standard deviations away from the mean. That if I take the absolute value of x minus its expectation, that quantity is greater than or equal to t times the standard deviation. Now in that case, if I integrate x minus mu squared over the entire sample space, since this is a positive quantity, I've got to get at least as large a result as I would get by integrating only over the part of the sample space that corresponds to the event A. And when the event A occurs, x minus mu squared is going to be greater than or equal to the square of sigma times t. This quantity has, by definition, the value sigma squared. It's the variance. This one has the value sigma squared times t squared times the integral dp over a, which is the probability of the event A. Sigma squared cancels out, and solving for p, we find that the probability of the event that the absolute value of x minus mu is greater than or equal to t sigma is less than or equal to 1 over t squared. With that result, I conclude this little video.